general topic, which is the application of linear and mixed unit programming methods to the optimization of business strategy, business-wide strategy, and the implementation of those strategies in a tactical methodology, which I'll provide an example of with a platform that's being developed and is available for both consulting and research activities here at La Católica. So just briefly, the topics to be covered will be just an introduction to the strategy optimization process, how it's normally done in industry using a method that's referred to as option analysis. I want to talk about some of the limitations of using option analysis. Then present a graphical approach to evaluating alternative strategies. Go into the application of math programming for producing these graphical outputs. Refer again to some of the technologies that are being commercialized, which are available, and their limitations. And then present a new approach, which is based on math programming. And I'll do that by using an example, which is this life of business optimization system that I'll be presenting today, that's being used in a number of projects worldwide. And then a few conclusions and final statements. So every business has to make some sort of strategic decision. If we're talking about corporate level, strategy is obviously to increase, or should be to increase shareholder value. But when we get down to the level of individual operations, we have to start talking about the nature of those operations and how they have specific strategic decisions which need to be made. Now, the driving goal for most operations is to increase value in some way. If we talk in terms of shareholders, obviously that goal is to increase shareholder or corporate value. But of course there might be many different types of stakeholders. And I've worked with operations in the past where the interests might be also aligned towards maximum recovery reserves and of course employment and regional development as well. But no matter how you're going to do this, there needs to be some way of evaluating each project in terms of what the operating strategy should be, what decisions should be made in order to, for instance, produce the greatest return on investment, that being the ultimate or strategic goal for the corporation. But in doing this, we also have to have not only a means of maximizing the value of the project, we have to have some means of quantifying the risk associated with the project as well. We need to know that our strategic decisions are also going to produce a robust plan for that project. When we do this, we have to recognize there are many different options in terms of what decisions we can make. Therefore, when we make a comparison between these options, the method that's used for that comparison must be consistent so that we know when we're comparing one cutoff to another cutoff, for instance, that the differences between the two are not a function of the analysis or the analyst, but are truly a difference between those two options in terms of their return on value. So all business in some fashion trying to seek a way of allocating resources to get the best overall return. At the level of individual projects, though, this allocation translates into specific strategic decisions. And most of what I'll be talking about today relates to the mining industry. But this is true for just about any business that has to deal with the allocation of resources. So the methods I'll be showing you today, even though they're quite mine-specific, they have general applicability. So if we're talking about the minerals industry, then strategy really relates to how you're going to deplete a resource. Basically what the reserve is going to be, how you're going to mine it, what methods are going to be used, and what products and what quantities are going to be produced and sold to whom. So the examples of typical strategic decisions made in the minerals industry would be cutoff, mine life, and capacity, one and the same. Any stockpiling strategies that might be used, the mining method or methods that will be used. And for instance, in an open pit mine, the height of the benches might be a strategic decision, as well as in an underground operation, the sublevel intervals would be a strategic decision. And then of course the access method, whether you're going to use a decline, a shaft, a combination of the two. And possibly there's many other types of decisions that have to be made that are more operationally specific to that particular project, such as whether you're going to use truck haulage or conveyors. The interesting aspect of strategic decision making is that they're difficult to reverse, and they often get made very early in the project's life. So possibly as early as a scoping study or a pre-feasibility study, someone, somewhere, in some consultancy possibly, has said, for instance, this is what the cutoff is. That defines the resource. And once you've published, for instance, what your number of ounces in reserve are, it gets very difficult, politically very difficult, to change those decisions. Because, of course, your reserve levels go down and there'll be a negative reaction from the investors, even if you have massively increased project value by doing so. So it's very difficult to change some of these decisions, and they don't get revisited very often. So when we're talking about strategic decisions, we're usually involving some revision of the reserves. We're talking about changing the mine plans, changing the schedules. Doing these types of analyses historically has been very difficult. It's been very costly in terms of manpower. They take a fair amount of time. They can be politically difficult to implement. And because of these problems, it's necessary to have some sort of methodology in place that speeds the process up, makes it consistent, so that we can compare options in a consistent fashion, and that also is defensible. So if, for instance, we have to go back to the shareholders and say, yes, we've raised the cutoff and we've dropped so many million ounces from reserves, but we've increased project value by 30%, which would not be an unreasonable number in the case of cutoffs, we have to have a foundation that is intelligible and accepted within the public on which to back this type of decision up with. The classical approach to option analysis is somewhat daunting. And we would start, for instance, in the case of cutoff analysis, by choosing some sort of measure of cutoff. Not necessarily a measure in terms of grams per ton or percentage. It might be a measure such as net smelter return or net smelter return per mill hour. So this in itself is a major decision, is what is the basis for cutoff. Once we've done that, we have to go on and we have to say, okay, this is what our resource looks like at a given cutoff. What will be the appropriate mining methods for that resource? And of course, there might be many different cutoffs we want to apply. And the resource looks different in each one of these cutoffs. We have to select one cutoff. And so usually we'll start with some reasonable cutoff, such as a marginal cutoff or a break-even cutoff. This gives us a resource model to which we have to apply some geotechnical constraints in order to better define the areas that we're going to mine and what they will look like. And of course, we don't really have a lot of information necessarily, and we have to pick some set of geotechnical constraints. And in doing so, we'll get a mining inventory. This is a set of possible stope shapes which we want to mine. One cutoff plus one set of geotechnical constraints generates one realization of what those reserves will look like. Once we have the stopes in place, we have to choose a method of access and put an access design in place as well. And there's many different possible access designs which can be used. We have to choose one. And this gives us a final mine design, of which there might be many alternative mine designs. To this we have to apply a capacity and a mining rate. And then we can put that into a financial model, a scheduling package, and from that we get a cash flow. And the cash flow gives us some sort of measure of what the ultimate value of that option is. And we return in the cycle to the next cutoff. And we repeat that. How many times? How much money do you have? So this is a very painful process. And because of this, strategic options in the mining industry are generally not examined in any great depth. We don't look at a lot of different strategic options. So what are some of the problems, in summary, of using our typical approach to strategic optimization, which really at this time is simply a matter of comparison of alternative options? First of all, we need engineers, geologists, hydrologists, geotechnical engineers that have a very wide skill set and can be very expensive. Also, as I showed you in that cycle, given a normal budget for a pre-feasibility study, we can't examine very many options. So whether or not we look at the right set of options or not is highly questionable. Also, we do a final analysis usually based upon a cash flow. The cash flow generates a rate of return or a net present value or some other measure of present value. But when we do the flexing to examine risk, usually the model that we're flexing is not flexible in terms of the schedules. So we might have an accountant, for instance, that's changing levels of capital investment and thereby levels of capacity without examining how that changes the schedule and the mineral that's produced. And we're using, as engineers, highly inappropriate levels of detail. The mining engineering public now doing option analysis is using packages where they do very detailed mine designs, where one mine design might take them several weeks, if not over a month. And that in itself is a very limiting factor, which offers very little additional valuable detail to the analysis. So in the end, it's no wonder that we don't look at very many alternatives. We don't look at a lot of different options. And as I said before, that probably means that we miss the optimal set of decisions, the optimal strategy. Now, a method of comparison, which has been presented in several other places before, there's nothing unique in this, is this idea of a hill of value, where you're looking at different values you can take for different strategic options and seeing what the response surface looks like. In this case, the response surface might be the net present value, and how the net present value changes as a function of more than one decision. So you want to see not only where the optimal point is in terms of what decisions should be made, but you want to look at the shape of that response surface. You want to know if your project is very sensitive to the cutoff grade, or whether the project is very sensitive to the capacity. So we refer to these as hills of value. And where the data comes from the hill of value is by generating a cash flow for each one of the options. And of course, behind the cash flow, there has to be a cutoff, there has to be a mining method, there has to be access design, there has to be an overall mine plan. So behind every option we select a value for, underneath that, there has to be a mine plan that produces a schedule, that produces a schedule of mining physicals and mining capital expenditures that we can use to generate, for instance, a net present value. What's very useful about these types of graphical measures is they give us a good feel on a corporate level for what the impact of different decisions are in terms of competing objectives and goals. So this topology that we're generating is a direct outcome of the mining physicals. And that has to come from an optimal schedule. Because if it doesn't come from an optimal schedule, then that surface can change. And we really don't know if we're making a true comparison between alternative strategic